Another episode on our integration calculus, and over the previous one we took it through integrating common functions. And this episode is going to be interesting because we're going to apply the integrations rules to various word problems, and then I call it story time. So we're going to take examples in all these merits of integrations. Let's take the first story. First story has to do with area under a graph. As usual, it says consider a function given as 600x minus x squared over a given interval. Approximate the area under this graph. Approximate the area under this graph. First, you want to know how the graph looks like. Let me change the pen to I think blue would do. From this given function, x is given in the interval 0 to 600, and so I have it here 0 to 600. When it's 0, I definitely go my function will be 0 because I substitute 0 into it. When it's 600, trust me, it's going to be 600 times 600 minus 600 all squared. This is the same as that, and hence I know I'm going to get 0 at the end of the day, right? But whatever is in between, you must find the values for all this. But I know the middle part 300 is going to be 80,000. You can try it out if I'm wrong or correct, and this will be your graph. This is how your graph would be from 0 to 600, and this is the maximum point. I'm not doing extremes here, but this will be your maximum point, 80,000, straight down to 300. You want to know the area under this curve. That is what the question demands. That is the beauty of integration. And I'm going to use a for the area f of x, and that's going to be from a to b f of x dx, because it's given in terms of x. What is the limit for a? Start from 0. A is your lower limit, 0, and then b is your upper limit, 600 of the function dx. By the sum and difference rule, I can break this down into these two separate things if you want it that way. And so 0 to 600 of this, and then 0 to 600 of that. Okay, and then integrate it separately. By the power rule, I'm going to get 600 over 2x squared over the limit 0 to 600 because it's definite integral, minus by the power rule I'm going to get 1 over 3s cubed 0 to 600. Alright, now still, since I have the power rule, the sum and difference, I could simply say that 600 600 over 2 should give me 300. Yeah, I'm very sure that 300s squared minus 1 over 3s cubed, all taking 0 to 600. Okay, so you know what to do. You substitute 600 into the upper limit and then 0 into the lower limit, and I already have my answer in my slide. You should confirm that I'll get 36,000 units cubed. It is in billion. Okay, so don't forget it's 300 times 600 all square. Let me take my time and do it right here. This will be equal to 300 times 600 all square minus 1 over 3 600 all cube, okay, to the first part, minus 300 times 0 all square minus 1 over 3 times 0 all cube. This is what I'm doing, and you know definitely all this part is going to go to 0, and what you will be left will be this part. That's going to give you the 36 million units cube for your area under the graph. As simple as that for integration. So that's my first story. Story number 2, we have a distance. We want to consider distance as an area, which is right. This is a very simple one. It says if a vehicle travels 50 miles per hour for 2 hours, how far has a vehicle traveled? I have my card drawn here as beautifully. It says it's taking 50 kilometers per hour. In a natural sense, that is how I would have solved the problem. If 1 hour is 50 kilometers, what is 2 hours? And so we normally go by if more or less divide. So 2 hours over 1 hour times 50 kilometers, right? And this is simply going to give me 100 kilometers per hour, and that is correct. But if I want to use integration, which is also correct, I'm going to tackle distance covered as an area. Okay, so what is the distance? Distance would be a definite because there's a starting point and there's a final destination of the function. what do you think my A would be? My A will start from a 0 initially when the car is at rest. There's no movement of the car, and so there's no velocity, there's no distance covered. And then my B will be the distance that can be covered, that is 50 kilometers per hour. And what is my function of the velocity? That is 50. Sorry, we are looking with respect to T. Okay, so it's not 50 upper here, it is rather 2. So the 0 means that at time 0 when the car has not moved yet, and then the 2 means the final hours the car was able to cover, with the distance of 50 dt. Why dt? I'm looking at time. Alright, but in the slides I think I use x, which is still correct, but mostly we use t for time, so you can do that correction. Let's integrate this by the constant property. If I integrate a constant, that is a constant times the function of integration, or the variable of interest. Now there's a limit 0 to 2. There's a finite or definite integral, and so I'm going to get 50 2 minus 50 times 0, upper minus lower limit, and that's going to give me 100 as I initially had. We want to use integration this aspect, and so realize that we've confirmed 100 miles or kilometers per hour. That is story number 2. And the third story is still something simple. We have a skateboard company, and says he wants to determine the price of 50 skateboard produced, but then the cost for production of one skateboard is $40. How many or how much, I don't know what to say. What will be the cost of producing 50 skateboard? And here you can still use if more or less divided approach, but let's use integration. Okay, so the cost will be from initial cost or initial production to the final production of our cost function. So what will be your A? Your A is going to start from 0. It means there's no production. That is what 0 means. I'm explaining anytime I use the zeros what it means. So in the second story, 0 means the car has not moved at time 0, is at rest, okay, to when it covered 2 hours. Here to 0 means that there's no production. So you can't just use any numbers, it must make sense, okay. When there's no production to when it has produced 50 of the skateboard, and what's the unit cost for each of them? 40. I'm going to use the X or the Q. So it means I'm setting Q to be the quantity, the number of skateboard that can be produced. If I integrate this by the power rule or the constant property, I'm going to get 40Q with the limit 0 to 50, and that will be equal to 40 times 50 minus 40 times 0, and 40 times 50 should give you $2,000. So you're going to incur $2,000 if you want to produce 50 skateboards. As simple as that. Here means that at 0 you're going to get 0. It means that when there's nothing to produce, there's no cost to incur, and that is the understanding we will have there. Okay, now to the last story of the day. That is story number 4. I hope that's the last story. You are looking at change in population in our marketplaces, in our workplaces, in our environment, in our society. Population either increase or decline due to some external factors. But let's see what we have here in our word problem. It says you go to a market, and then the population, the change in population is increasing exponentially given by this factor. It is increasing exponentially by this factor given respect to time, and the time for this model, it was accumulated during 1960. So I use T0. So there's the initial time when this population was first estimated. It goes ahead to say that in 1980, so we have another time given T1. In 1980, the population at the market was 790,000. Is that right pronunciation? 790,000 people at the market in 1980. So what is the time difference here? 60 to 80, I think it's 20 years if my calculation is right. But we're not given the population initially, but we can still have it. It says estimate the population model and then estimate the population that will be in 2012, sorry. So let's start. I have my change in population model given as this. Because of the positive exponential, means the population keeps increasing from 1960 to 1980. I expect it to increase in 2012. It means it should be greater than what we had in 1980. If that is not your final answer, then there's something wrong. Okay, so you always want to have the final answer before you even start to work towards the goal. What can I do here? I can simply multiply through by the t, and then I have 1.17 exponential 0.260 the t, and I integrate both sides. 1.17 exponential 0.2 the t. I told you there's a relationship between derivative and an exponential function. Okay, and so this gives as if I have 1 here. So if I differentiate a constant, it is just the constant times the variable of interest p, and so simply I'm going to get p of t is equal to, don't forget this is small change in t, probably I should bring it there not to confuse anyone. So p of t will be equal to, if I integrate exponential function, what happens? I differentiate what is up here and I divide 1.17 all over 0.26 exponential 0.260 plus the constant of integration. Why? Because there's no limit attached to the integral sign. So you differentiate the exponent part here and then you come and divide by it. This is our population function. That is question 1, rightly answered. So if you have any time, you can always estimate the population. So if I ask to find what is the time at 1, you realize that you're going to get some values here plus the c. How do we tackle the c? That is a question. It has to be dealt with. It means that we are not done solving for the model. We can only find c if we have some initial condition of the problem. Initial condition can help us cater for the c. And so what is this initial condition? We were given the initial population time 0 to time 1, 1960 to 80, and I said the time difference is 20 years. Okay, it means that we can tell in 20 years too, it gave us 790,000. Okay, so we have this. So it means that p at 20 will be equal to, if I divide this, I'm going to get, if I divide this thing here, it's supposed to give me 450 exponential 0.260 plus c. But wherever I see t, I place 20 in. Okay, so p20 was 790,000 is equal to 450 exponential 0.26 times 20 plus c, and I can simply find c by saying c is equal to whatever I have here over my 450 exponential 0.26 to 20, and that should give me 33.1. There's no unit to this. By applying the initial condition, I can now find c. This means that my population model is actually 450 exponential 0.260 plus the c, which is now 33.1, and this is the right model. You realize that with this, I can find a population at any given time. If you want to test that this population model is right, you want to first look at the 20 years. You should get back your 790. If it doesn't work, it means your model is wrong. But now let's find estimate 2. For estimate 2, it says what is the population in 2012. You can't say p at 2012. It's not right. This is not right. Okay, so we have to find a time difference. It was 1960, we moved to 1980, and now we are in 2012. Between here and here, it was 20 years. Now between 1980 to 2012, how many years have we covered? It's 52 years. And so it means that to find a population in 2012, it is simply a population at 52 years. And that should give you what? 1772. How did I get 1772? I substitute 52 into this model. And so you can use your calculator and verify this answer for me. You realize that it is indeed greater than, so there's thousands addition, there's 1,000 added to this. You want to, this indeed greater than 790, that is in 1980. If you don't get greater than this number, there's something wrong. Why? Because the population model is growing exponentially. It is not decaying. So that is our final answer for the day. I think I have one more. I thought that was the last example. So let's take the last example here. The height of a thrown object. You can have a ball thrown in the air, you can have anything thrown in the air. And this picture talks about a football game where someone just kicks the ball up. You want to determine the height of the ball from wherever it was kicked off. From the word problem, certain things are given. So it says there's an initial velocity given. If you read it very well, initial velocity, I'm going to use v naught or v at 0. T is time. So at time 0, it is 50 feet per second. And the initial height where it was kicked off, the initial height here was 10 feet tall, and then the initial velocity was 50 feet per second. I hope my handwriting has not been bad. Okay, so h naught or h at 0 was 10 feet, and then the velocity at any given time was given by this model in seconds. The question says A, determine the distance function at any given time. That's what we want to find. H. When you are done, determine the velocity and then the height after 3 seconds. These guys here, what do we have for them? You want to determine the height of the ball after 3 seconds, and then the velocity, the speed at which this ball is just moving after just 3 seconds, not in minutes. Okay, because in football it will not be kicked for a minute. It's just a few seconds, and then by gravity the ball falls unless someone hits it. So let's take the solution here. You want to start with your velocity. If you know the relation of a velocity between velocity and height, you know that velocity is the change in distance with respect to time, and so this is the same as the h dt. Okay, our interest is to find h of t. That is what we want to do. So I can quickly multiply through by the dt and have the h here. And what do I do? H with respect to time, I integrate both sides. So v of t dt is equal to integral of dh of t. Okay, and I know my vt was given as 32 plus 5 dt. Am I right? 32t. Yeah, I missed the t here. Plus 5 dt is equal to integral dht. Okay, so that's our integration. This as if I have a constant one here. It means I'm going to just have h of t. I've explained that in the previous example. Now if I want to integrate this by the power rule, I'm going to get negative 32 on 2t squared plus 5t. Don't forget your constant of integration. Let me want to simplify this. I'm going to get negative 16t squared. You know why? I'm dividing through by 2 plus the 5t plus the c equal to h of t. As simple as that. I found my function at t. Either I leave it here or I go ahead and find this constant term, because I can't find the height at 3 seconds whilst this variable is still in place. So again, we employ the initial condition given. Initial condition was the height at 0 seconds was 10 feet from the floor or from where it was kicked off. And so wherever I see h, wherever I see t, I put 0 in it. So negative 16 0 squared plus 5 of 0 plus c is equal to h of 0. So I know this is equal to 10. Here goes to 0, here goes to 0, and so c is just 10. As simple as that. It means that my height function is actually 16t plus 5t plus 10. This is now the right height function, and then I can find the height of the ball after 3 seconds by just substituting 3 in it, and you should get 16 feet. But that is not all. We want to also find the velocity after 3 seconds. Now velocity was the h, the t. So what do? You differentiate this guy here, and that's going to give me negative. It's no more integration, but now we are moved back to differentiation, and I love this. Negative 16 plus 5. Am I right with my substitutions here? I think okay, so there's a square. Yeah, let me move back here. It's a square from here. That makes it cool now. So it means I'm going to get negative 16t because I'm differentiating. No. Derivative by power will give me negative 32t because I have to multiply here by 2 plus 5. This is my new term. Yeah, I'm very certain about this, unless I'm wrong. So now I can find my velocity at 3 seconds. That will be negative 32 times 3 plus 5. That should give me negative 46 feet per second. Why did you think we have negative? It is not wrong getting negative. I've explained the phenomenon here. The ball will have to just fall back. If there's a decline in velocity moving reverse form is negative. If velocity is moving in a forward position, so it's like forward and then backward. Forward is positive, backward is negative. It's like driving a car, you're moving reverse. So when the gravity is falling, it's coming with a negative velocity. So this is right. If you get a positive velocity, it means it's still moving in the air even after the 3 seconds. That is also possible. That's also possible anyway. I think that is it for the day. And so intuitively we say the ball is 16 feet above the ground, which we had here. That is after 3 seconds. But then the ball moves down after the 3 seconds due to a negative velocity. I think I'm done here. Now to the wonderful moment of our lives. That is a problem of the day. You want to get all these things we've done into this, solve it yourself, and then let's comment our answer in the comment section. So let me help you analyze this. There's a river, there's a lake, and then there's this factory producing some pollutants into the lake, directly into the lake. So the solid guys here are the pollutants, okay. But we are being given the small change in pollutant at any given time t by this equation, 280 t to the power 3 on 2. The question is, how many pounds of pollutants enter the lake in 60 months? As I say, we are looking at time in months. After 16 months, what do you think will happen? Do we have a decline in pollutant or we have increase in pollutant? You must think of it before you start solving. You must think of it before you start solving. Assuming there's no treatment of the pollutant in the lake, you expect it to grow. Okay. And then it says, at what time do you think the pollutant will get to 50,000? Or that's not what the story says. Yeah. If you want to advise the environmental agencies on when to begin cleanup, when you can get 50,000 pounds of pollutant, that's so much. Okay, so let's see how we can solve the problem. You know, if I want n of t, it means I have to integrate my small change function, and you can simply get your answer here. As simple as that. Okay, then you can find the pollutant after 16 months by substituting 16 into whatever function you are going to get here. Now the next question. Now nt has been given to me 50,000 with whatever functions you get here. It would always be in terms of t, and you're asked to find t. So from here, I have this diagram. This skeleton has not been confusing. if you get a function here, then you can make your change of subject to get a t. And don't forget, we're dealing with time, and so you can never get negative time. It should always be a positive time value. And then check if your time is right or not. So this brings me to the end of our storytelling with integration. In the next sessions, we are going to take special techniques for integration, that is by substitution, by part, and then by partial fractions, which we dealt in algebra. I love this, all the fun. So stay tuned, and then let's enjoy the moment together. Thank you very much.